Hi, my name's Sitara Uppalapati.
I'm Ryan Brown.
And I'm Alexander Nelson-Groocock.
Today, we're going to be presenting on our predictions for the growth of COVID-19 infections in the greater Austin area. But before we jump into our data analysis for this project, we would first like to touch on some general statistics. This slide includes the total cases and total death statistics for Austin, Texas, and the US. Focusing specifically on Austin, we can see that there are 49,535 total cases and 726 total deaths. Now, moving on into our data analysis, we first started out by doing some surface level analysis using raw data from the Texas Department of Health to visualize general trends. The graphs on the slide show total COVID tests over time, the cases over time, and deaths over time. And from these graphs, there are a few notable trends that we have observed. We first observed that the number of active cases is steadily declining, and we also observed that the cumulative cases, looking at the graph for the MSA, Austin follows the logistic curve that is seen in most cities and nations exposed to COVID-19.
As shown in the graphics previous, the cumulative case counts in Austin have been shown to follow the logistic curve. The curve is commonly seen throughout cities, states, and nations that are exposed to COVID-19. In the top right-hand corner, you're looking at the curve for the cumulative case count in China. This specific curve tracks China from the first COVID-19 case to when COVID-19 was declared eradicated. We can see how closely China follows the logistic curve in this case. With this intuition in mind, we consulted academic literature and found that the logistic curve is very commonly seen when modeling disease outbreaks in general, not just COVID-19. We also discovered that CDC guidelines were crafted to create a logistic curve in the United States in a sense, and our later analysis confirms that Austonians are generally following these CDC guidelines. These three justifications provide us with enough reasoning to continue modeling with the logistic curve.
The SEIR, or Susceptible, Exposed, Infected, Removed model, is commonly cited as being the premier disease prediction model. It models people following the path of being susceptible, then exposed, then infected, and then removed through immunity. The main determinant of the curve is the transmission rate because sigma and gamma are biologically fixed. In creating an SEIR model, we would be trying to fit to the cumulative case data for the Austin Metroplex by modifying the ERR, which is the effective reproduction rate, as a function of time. As you can see on the right, the SEIR produces a logistic curve anyways when we're looking at cumulative case count, but since we're not fitting it directly to the data like we would be with a normal logistic growth model, we end up having a worse fit, and both of these models anyways run into the same problem, a problem that Alex will now discuss.
We can verify again that the Austin area's cumulative case count does follow the logistic curve in the left-hand graphic, but there's a notable break from this logistic curve as indicated in the right graphic. This is where our model gains the most traction and allows us to make more informed predictions about COVID-19 infections in the Austin area over the winter period. By layering the logistic regression curve over the real data from the MSA Austin area, we can more clearly see that there is a divergence. On the far right, you can see this divergence occurs on September 1st, or step 225, and it is linear in nature. This linear trend, after being verified, allows us to bake in additional factors into our model beyond just COVID-19's infectious rate, transmission rate, and incubation period. After noticing visually the linear relationship, it was important to verify this linearity statistically if it was going to serve as the basis for our factor model. We performed 4 fundamental checks for linearity, excluding the collinearity check because we're not using a multiple linear regression. We first amplified the point of inflection where the linear trend began and saw no significant skew, kurtosis, or outliers. Second, we plotted the residuals of an ordinary least squared linear regression on a QQ plot seen in the middle top and saw no significant outliers and generally evenly distributed error terms. Third, we conducted a linear rainbow test to check for linearity on the micro level of our data. This produced a t-statistic close to 0 and a p-value less than 0.05. Thus, we could reject the null hypothesis that there was not a linear relationship. Fourth, we conducted a linear Harvey-Kohler test which allowed us to see convexities and concavities in the data on a macro or micro scale, and this produced a t-statistic close to 0 and a p-value below 0.5. Thus, we could accept linearity.
The previously identified divergence at step 225 aligns precisely with an inflection point on this ERR graph from RT.live. The proven linearity of cumulative cases matches the stability of the ERR that you see in the close-up on the right. The fact that it stabilized near 1 further confirms our linearity assumption because it means that infections are neither spreading more quickly nor more slowly. The lack of significant events or changes coming in the period leading up to the holiday season and the stability of the effective reproduction rate mean that we can safely assume the predictions made by the calculated linear regression shown above are valid until the holiday season. Going into the holiday season, we see 56,770 cases on November 25th. Looking forward to the holiday season, the best case scenario would be that the rate of infection doesn't increase, and we see a linear growth in the cumulative number of cases consistent with the previously calculated linear regression. This would mean that by January 1st, there are 61,645 cumulative COVID cases in the Austin Metroplex, an increase of 4,875 over the holiday season. Unfortunately, this case is optimistic. The holiday season brings changes in travel and shopping that can increase the infection rate.
Therefore, next we realize the importance of modeling in factors that are key to the holiday season. We've categorized these factors into 2 main groups, travel and shopping. For travel, we looked at raw data for ground travel, including cars and bikes, and air travel at the Austin Bergstrom International Airport. For shopping, we looked at statistics and used our model to extrapolate the number of in-store shoppers and possible cases resulting in increase in COVID-19 cases.
We needed to find a proxy to see if people were living their lives as normal, if their behavior was still being affected by COVID-19. We used a data set produced by the city of Austin that tracks traffic reports, for example, collisions or hazards. We believe that this accurately represents people's movement around the city because as streets get busier and more people start to go to stores or go to eat, reports would increase. Our hypothesis was verified by the graph in the top left of the screen, where we see a significant drop-off in the number of reports once COVID-19 entered the United States, and then a slow tick upwards before flattening out. We used step 650 as the cutoff between pre-COVID and COVID time periods. Calculating the average number of reports in a given 5-day period, we found that there had been a 50% decline. For completeness, we then created a linear regression modeling into the future and saw that generally it was a flat slope. And then again, we verified our linear assumptions using residuals and the linear rainbow and Harvey-Kohler tests.
Next, we also used raw data from the city of Austin to analyze Metro Bike Rides, a public biking program, and we believe this is a good proxy for people's movement outdoors in addition to the car traffic Alex mentioned earlier. We also analyzed air travel, and we believe that combining both ground and air travel will provide a more complete picture. And here we've observed a 70% decline in total passengers passing through Austin's International Airport. And after analyzing historical data, we also noticed that the number of passengers traveling during the holiday season does not significantly increase from previous months, and we kept this information in mind. We also looked at shopping, a hallmark of the holiday season, and we realized that 29% of adults are likely to shop in store for holidays. And taking this 29% number and using the number of adults in Austin, we arrived at 214,941. And taking that to the number of cases, we arrived at 446 by doing statistical analysis.
In the worst case, the holiday has a similarly drastic effect on infection rate as ending the lockdown on May 1st did, based on all the previous factors that Sitara and Alex described. To quantify the increase in infection rate, we looked at the increase in slope, which was 25.73%, and we applied this to our slope. The worst case also includes 446 additional cases from the increased shopping. So in our worst case, we have an increase of infections of 6,720. In the best case, we have 4,875. And in the medium case, we have 6,274. In all of our cases, we believe that Austin has established a COVID-19 personality, and individuals will not significantly deviate from their routine based on the holiday habits, supported by the statistic on the bottom left. Thank you.
Okay.